Okay, so just to recap from this morning, we looked at how we can use Bezier curves to draw nice, smooth lines. Most of the stuff we've been dealing with graphics up until now is all about straight edges, polygons, straight lines, etc. Well, obviously in graphics, we also need a method or means to draw curvy lines, and Bezier curves allow us to do that. So here we've got some examples which we saw this morning of the cubic Bezier curve. So cubic Bezier means it's a polynomial of degree 3, and therefore we need 4 points to define our curve. And here are just some examples which I showed in this morning's lecture. Right, and I'll come back and talk a bit more about the assignment later on. Okay, so what we're going to look at now is extending the Bezier curves to 2D or 2 or 3D, whatever way you want to call it. And Bezier curves can be extended to create what we call a Bezier surface, or also known as a Bezier patch. Okay, so Bezier surface or Bezier patch means the same thing. With the Bezier curve, okay, we have a parametric equation in terms of the parameter t. Remember, t was in the range 0 to 1. The more values of t you have, the smoother your curve is. The surfaces are defined by 2 parameters, and I call them u and v, just to be different from the t. U and v are both parameters in the range 0 to 1, but we have 2 of them now, okay, because we've got them in 2 dimensions. And essentially, the mathematics is very similar. Uses Bezier curves in x and y directions. So if you imagine, if we're looking down on our patch, if you've got a 2D patch, it's going to be in the x and y directions. And we can have different degree curves in the 2 directions. So for example, you could have a cubic in the x direction and a quadratic in the y direction. If you have a Bezier surface of degree mn, where m is the degree of the curve in the y direction and n is a degree of the curve in the x direction. Okay, yeah. So when we talk about degree of the patch, we talk about both degrees. You stop talking about it. Right. So we have control points. Because we're extending to 3D, we not only do we have x and y control points, we also have z. Okay, so our control points have 3 coordinates. Okay, and what they're expressed as they're expressed in 3 separate matrices. Okay, so this is your control point for the x coordinate, control points for the y coordinate, and control points for the z coordinate. Okay, so if we're in 1D, let's take the first row. We just have a load of, 1D, 2D. If we're in 1D, we just have a load of x coordinates. We just have a row. Okay. Because we're in 3D, we've got a matrix. So imagine looking down on this. We'll have, for example, if we had a 4x4 matrix, we'd have 16 control points. Okay, so those are our control points. So we have a matrix each for your x coordinates, y coordinates, and z coordinates. Okay, and this is how we calculate the Bezier surface. Now, don't worry about this. I'm not going to ask you to do this. Okay, this is purely theoretical. I'm not going to be asking you to apply it for your assignment. But it's not too difficult. You should recognise this bit within the square brackets. That's your Bezier curve. Okay, so the Bernstein polynomials are the same from what we did this morning. And they're in terms of the parameter u, and that's multiplied by your control point. Okay. Ij are simply the Ij sort of addresses or indices for these matrices. Okay, so the one within the square bracket, okay, that is a Bernstein, that is a Bezier curve in one direction. And we also have it sums, an outer sum, with another Bernstein polynomial there, and that's summing it in the other direction. So one I equals 0 to m, that is going down that direction. Okay. J 0 to n, that sum, is going. Sorry, is going across. So combining those two sums combines the x and y direction. Notice the parameter, so the one from the y direction or the x direction, whichever one, doesn't really matter, is u and v, and we do the same for each coordinate. This is our x coordinate, our y coordinate, and our z coordinate. So essentially, to cut a long story short, this is just applying Bezier curves in both directions. Okay, how do we calculate it? Well, like with Bezier curves, we can write it in form of a matrix equation. So this is different from just the curve. What we have here is we have a row vector of your parameters u. If we had 100 parameters of u between 0 and 1, we'd have 100 numbers going down. So each of these sort of columns across will have loads of values of u going down. Then we have M, which is your Bezier matrix. Then you'd have your x coordinate for your control point. Then you had an N. Now N is also the Bezier matrix, but we could be using different orders in the x and y directions. Okay. And then we got our parameter v on the right hand side. So u and v are just parameters between 0 and 1. So if we had a degree 3-3 Bezier surface, which is the most common, M and N will be the same matrix because we're using the same degree in both directions. So this is from earlier. This is our Bezier cubic Bezier matrix, and you can see that's the same. Because it's cubic, we've got u cubed, u squared, u and 1. Likewise on the right hand side. Okay, so if we multiply all these together, we get our x coordinate for the parameters u and v. Okay, so there's the MATLAB code. So that's your mathematics. We transpose that to MATLAB. Okay, not too tricky. So here I've got a function called Bezier surface. The x, y, and z coordinates of the control points are stored in separate matrices, and u and v are just the parameters like t was. Okay, define M. Your u and v arrays. Notice I've got a little transpose here. Okay, so that's transposed because this is a row and that's a column. Okay, and then I just multiply them all together to give me my x, y, and z coordinates on my patch or surface. Okay, so here's an example. What I've got here is I just said, okay, randomly give me 16 coordinates. So I've got a patch. Okay, so my x coordinates, my px, are between 0 and 1. It doesn't have to be, I'll just, for ease of use. My y coordinates are between 0 and 1. And I've randomized the z, so the heights have been randomized. So the x and y I've sort of fixed. I've got them in a square configuration. Y is randomized. Okay, and all I've done here is apply Bezier curve, and you can see that given 16 control points, gives us a nice smooth curve. What actually I'm going to attempt to do is just show you this working on MATLAB. So this is the code that actually does the work. Okay. Doesn't always give us a nice one, but there we go. So this window on the left, what I'm going to do is just tilt this up a bit so I'm looking down on it. Okay, you can see that's like a square configuration. So I've got my 16 control points, 1, 2, 3, 4, across, 1, 2, 3, 4, up. So the x and y coordinates of those control points I've fixed, and all I've done is I just asked for it to give me a random height. Okay. So if I view that from like that angle, then this is the patch which results. So what was it? It was for somewhere like that. Okay. And that's the patch. And I'll just give you a sneaky peek at the code. So you can see this is calculating. So px and py are just calculated from linearly spaced x and y coordinates. Pz is just random. Generate my parameter values. Well, here I've just used in steps 1/10, which is quite large. If I take that to 1/100th and run it again, you can see it's giving me a really smooth one. Okay, you can see how much sort of that's changed. Okay, call the Bezier surface, and that just plots it. Okay. Right, so that's. I hope you can see that allows us to make nice sort of, especially in 3D, nice sort of smooth objects. Indeed, the teapot, which we've been looking at, when you go online, you can actually download the data for the teapot, and the data comes in this form. Because these are control points for the Utah teapot, which you've seen before. All I've done here is applied the Bezier patches to those control points. A couple of things you might notice. Look how angular these things are, especially that sort of spout goes way. The control points go way back on itself. But when you actually apply it, it looks okay. So this may look a bit weird. That's because that is the data you get. You can download this online if you search for it. The data you get is in that form. Apply the Bezier patches, and you get your teapot. As I said, it's not something I'm going to be asking you to do, but it's just an extension of those Bezier curves. Okay, so what now I'm going to talk about is B-splines. Now, B-splines extend the Bezier curves, and the reason why B-splines are useful is they allow us to create long, wavy lines. So if you remember, at the very beginning of the last lecture, I said a quadratic curve can only have one change of direction, a cubic can have two changes of direction. Well, what if you want a curve with lots and lots of changes of direction? Okay, well, this is where B-splines comes in. Now, B-splines essentially are several Bezier curves joined end on end. Okay, and the word B-splines is short for basis splines, which I'll explain about in a minute. Now, the relationship between the number of control points and the degree of the B-spline is not the same as a Bezier curve. Now, the Bezier curve, if you had a degree n curve, you need n plus 1 control points. Well, in B-spline, if you've got a k degree curve defined by n plus 1 control points, you'll have n minus k plus 1 Bezier curves. Okay. So let's say we've got a quadratic curve. Actually, no, let's use this example. Let's say we've got a cubic B-spline, so k is 3, and we have 6 control points, P0 to P5, so n is 6. Oh, sorry, so n is 5 there. Okay, so you've got 6 control points. N is the subscript of the last control points. We always assume the first control point has a subscript 0. Okay, so n is 5. So 5 minus k plus 1 gives me 3 Bezier curves. So what I've done here is I've plotted just any sort of, doesn't really matter, I made these up, P0 all the way around to P5. And I've also plotted some Bezier curves using B-splines. And you'll notice they don't join up to the end. Okay, and I'll explain about that now. But that's the basic premise behind B-splines. They're just Bezier curves joined end on end. So because we're joining Bezier curves end on end, got a few assumptions to make. The final point on the first Bezier curve have the same coordinates as the first point on the second one. In other words, where one starts and finishes, the other one starts. The first derivative at the end of the Bezier curve, i.e. what is the gradient at the end of the Bezier curve, is the same as the first derivative at the start of the second Bezier curve. So what that means is there's no sort of spikes or no sort of abrupt sort of kinks in our curve. Okay, the curve should just flow smoothly on. This is known as C1 continuity. And we also have the same, but for the second derivative as well, known as C2 continuity. So those are the assumptions in the derivation of B-splines. Okay, and this is the equation. It looks very similar to the Bezier one. Okay, so it's just, I've called it S for spline. Okay, and it's a sum of 0 to n. Remember, n is a last control point, 0 is the first control point. So pi, or your control points. And we have this nik function here. With the Bezier curve, that was a Bernstein polynomial, you know, the bin. With B-splines, this is what we call a basis. Okay, so nik are the basis functions, hence we call it basis spline or B-spline. And nik is given by this formula. Okay, it looks complicated, but if we break it down, what we have is we have a parameter t. Now t is not, for basis splines, is not in the range 0 to 1, not necessarily in the range 0 to 1. Okay, what we have is t is related to some values of t subscript I. Now, where you've got a subscript, these are called knots. Okay, so I'll talk about the knot vector in a minute. But think of ti and ti plus 1 as just some number. Okay, and they're increasing in value. Your t is your parameter. Okay, and that's the parameter there. So we have two expressions. Remember that 0 means this is your control point. So remember the ij notation from previous lecture. So for the ones on the far left of that triangular sort of scheme, which is this, okay, so these values here are determined by this case statement. So it has a value of 1 if this logic statement is true, or 0 otherwise. Okay, it's like a switch, an on-off switch. For all other cases, we have this nasty function here. Well, it looks nasty, but it's not that difficult. Okay, so in Bezier curves, we looked at de Castigl's algorithm. Well, this is the same thing with the B-splines. Okay, this over here, this N0K, this is your point on the B-spline. Okay, that is your coordinate for the parameter t. On the far left, these are related to your control points. Okay, so the same way as we did for the B-splines, we have this triangular scheme where the horizontal coordinate, okay, gives us is that coefficient, and the diagonal coordinate is that coefficient. Okay. Now, what are these t subscripts? Okay, these t subscripts are called knots. Okay, so the values of t subscript I are from a sequence, and this is called a knot vector. And what we have is your value of your parameter, which is different from the knots. Unfortunately, they're both called t in most textbooks. Yeah, there we go. T for the Bezier curve was in the range 0 to 1, but T for B-splines is in the range from the smallest knot to the largest knot. Okay. You can set whatever knots you want, as long as each knot is bigger than the one previous. Okay. Now, the knots that T lies between determine the basis functions. So if I'm just moving back a slide, for example, T, when our value of T is greater than that knot, but less than the next knot, that will determine whether we turn this basis off or on. Think of this as turning it off or on, any of these. Okay. The number of knots in T is n plus 1, is related to the degree k of your B-spline and the number of control points by this. Okay, so if you had a cubic B-spline using control points P0 to P4, so there are 5 in total. So n is 4, k is 3, plus 1, so we're 8. So we need 8 knots. So it's those 8, so basically we need 8 numbers, and numbers have got to be increasing. So simplest one is 0, not 8, we need 9 numbers because start at 0, end in M. So you might as well start at 0, end in 8. I could have started at 1 and ended at 9. I could have started at -9 and ended at -1. As long as they're, one of each number is bigger than the number to its left. Okay, so this is a not vector. Okay, so let's have a look at a quadratic B-spline. A uniform B-spline means the knots are equidistant. So, for example, here, each one is one more than the last. So a uniform quadratic B-spline, let's say it's defined by those 3 control points. Okay, so if I calculate how many knots I need, M is 5, so I need 6 knots in total. This M is the subscript of the last knot. So that's got subscript 0, that's got subscript 5. So I need 6 knots in total, so therefore those are my 6 numbers. And the B-spline curve is defined by this. Okay, so I equals 0 to 2, because that's my upper control point. And I have this summation, and using what we call the Cox-de-Boer recursive formula, I have the triangular scheme. And what I'm going to do is I'm going to evaluate the basis function. So what I've got is here, starting at this one is made up of a combination of those 2. Okay, so we have this horizontal arrow is given by t minus the first knot divided by, and I can't quite remember this one, so t minus ti, ti plus j minus ti. So that's that first coefficient. So that's what that comes from. Okay. And that's multiplied by n01, see? And then I've got the other one, which if you look back at the Cox-de-Boer formula, I can't remember off the top of my head, that's what you get. Okay. Well, these 2 are also, those 2 are also made up of these 2. So we then have to put those 2 in as well. This n01t here is the contents of that square bracket. This n11t is the contents of that square bracket. Okay, quite a lot of algebraic manipulation involved. Okay, if you want to do the algebra, feel free. You won't be tested on it. Okay, and that gives us this basis function here. Okay, now the values of these n's here are going to be either 0 or 1, depending on the value of t. So it kind of like turns each of these terms off or on. So when t is between the first 2 knots, the knot at 0 and the knot at 1, n00t is just going to be 1, and the rest are going to be 0. So if that's 1 and all this is 0, we just got a half times t squared. Else, if t is between the second and third knot, okay, n00 is going to be 0, the second basis function is going to be 1, and the final one is going to be 0. So it's like turning them off or on. And if you calculate this, so that's going to be 0, that's going to be 1, that's going to be 1, and that's going to be 0. You get this function. And between the third and fourth knot, get something similar. Okay, so depending on where that parameter is, depending on which knots it's between, you'll have different bases. Now, if you do similar for these 2, if you've got a second, if you just turn right back to the appendices at the back, I've actually done this for you. If you're bored one Saturday night, feel free to read it. It's quite boring algebra. It took me ages. I was going to put it in the notes, but it just bored me. Okay, so there's a lot of algebra which has gone into this. Okay, not difficult algebra, it's just time consuming. But what we have is we have these 3 bases. Okay, and where our t is, between which of the knots, it depends upon what our basis is. So for the first basis, it could be 1 of 4, depending whether our T is between which knots. The second base is again between 1 and 4. Okay. And what you should notice is these are actually quite similar. So here, where I've got T minus 1 and T minus 2. Here, where I've got T minus 1, I've got T minus 2 and T minus 3. So again, here I've got T minus 2, but here I've got T minus 3 and T minus 4. Okay, so they're actually copies of each other, just moved along to the right. Okay, and that's what they look like on your graph. Okay, so on the bottom I've got T, and there's my basis function, and if I graph each one of those, you can see they're the same bases, just moved along to one. Okay, so that's your bases for the quadratic. Okay, at that point, what I'm looking for is, in order for our B-spline to be defined, we need all three bases to be non-zero for a particular value of T. So for example, down here, only the red basis, okay, that one is defined here, non-zero. Between 1 and 2, only the red and green are defined. But between 2 and 3, I've got all three of them defined. So what I'm saying is, between these black lines is where my B-spline is defined, which isn't a good thing, because we've got all this values of T, and our B-spline is only defined between 2 and 3. Okay, like with Bezier curves, it comes a lot easier when we specify our B-splines in terms of matrix equations. Okay, so this is what I've done here is I'm only concentrating in this region here. So where our values of T is between 2 and 3. Okay, so those are our basis functions. Okay, and if I expand each of these out, I get this matrix equation. This is exactly the same as the Bezier curves this morning. Okay, so T minus T2 squared, or T2 in this case is 2. Okay, so if I replace T2 by 2, T minus 2 squared will give me 2 minus 4 plus 2, divided by 2 there to take out a common factor. Okay, so that's our basis spline. Very, very similar to the Bezier curve, and it's applied in the same way. Okay. In general terms, okay, what if I had lots more knots? So what if, instead of having knots 1, 2, 3, 4, 5, what if I had 20 knots? Okay, this area where it would be defined would be a lot greater. So in general terms, the knots, depending on where the knots are, will depend on our control points will change. Okay, so if we were going a long one, we'd be using different 3 control points. Okay, so that's a general form of a uniform quadratic B-spline curve. Okay, always best given by example. Okay, so here you are. Here's the MATLAB code. Again, define M, define T, exactly the same as Bezier. Calculate N and K. I don't think I need it. Oh yes, I need K here. Okay, so N is the number of control points minus 1. Okay, so the size of P along the second dimension minus 1. Loop through basis functions and calculate B-spline curve. Okay, so what I've done here is I've started off with an empty spline, and I calculate the current Bezier section. So here, when I is 1, I'm using the first 3 columns of P. And that calculates the Bezier curve, and I just add the Bezier curve to what is an empty spline. When I is 2, I'm using the second, third, and fourth control point. Okay, and then I'm just adding it to the end. So it's lots of Bezier curves just added together. Okay, and that's what you get. Okay, I've got the demonstration on MATLAB to show you. Dual B-spline. Okay, I want a closed B-spline. Okay, so I've written a little program which just allows me to click. Okay, so the first 3 control points there, it's not enough to define a Bezier curve yet. Let's click down there. So now I've got a Bezier curve, but notice it doesn't extend all the way to the end. So if I just keep sort of randomly clicking, you can see, but the blue curve, oh, this is running a bit slow. I'm going to stop it there then. Okay, you can see as I was randomly clicking around, it was generating the Bezier curves and sticking them on the end of each other. But notice it doesn't quite extend to the end. And that's because, if I go back to the slides, the reason it doesn't extend to the end is because it's not fully defined outside of that range. Okay, so that's a bad thing. The fact it doesn't extend to the end is a bad thing. There you got it. Okay, so in this particular example, between knots 2 and 5, I have a B-spline defined, but outside that range, I don't. Okay, this is where what we call open uniform B-splines comes in, and these are the most common. When people talk about B-splines, they mean open uniform B-splines. And this gets over the fact that using uniform B-splines is undefined outside of the range. So all we do is we set the first k knots, which is T0 to Tk minus 1, to be equal to Tk. Okay, so let's say here I have a knot vector with 8 knots in it. Okay, so it's a quadratic B-spline, so k is 2, and I've got 5 control points, so n is 4. Okay, so m is equal to 7. So I've got 8 knots. Now k was 2, so the first 2 knots are going to be the same value as tk. So I've set tk to be 0, T2 to be 0, T3 is 1, 2, and 3. And the first 2 knots, I'm just going to set to be the same value as whatever that is. So that's 0, so I pad it out with zeros. Likewise, at the other end, the last 2 knots are equal to that knot there, T5. Depending on the degree of your B-spline, will depend on how many knots you have to pad. Okay, that's all you do. So the first 2 knots are the same as that knot, and the last 2 knots are the same as that knot. That's all you do. And if you do the calculations of basis functions based on that, again, lots of algebra, lots of fairly tedious algebra. It's in the appendix if you really want to look at it. This is what you get. So one thing you notice is this red one here, that's the same as what we had before. That's a nice symmetric basis function. All the others are asymmetric. So the blue one, okay, you can see is asymmetric, and that has a mirror image at the right-hand side. And the green one, you can see sort of like a gamma curve, and has a mirror image of the sort of mauve one there. Okay, so that's the open uniform. If I was to sum across all those values of t, I get a flat line at 1. Okay, so if I take any vertical line across here, add up the values of each of those basis functions at any vertical line, you get 1. Okay, so having a look at the matrix form. Okay, so what we have in the middle is what we had before. Okay, that was from our previous example. For the first 3 control points, we have a slightly different matrix. Okay, but it's calculating exactly the same. And for the last 3, we have a slightly different matrix still. Okay, so these are 3 matrix equations, depending on whereabouts in the knot vector we are. Okay, so there's the MATLAB code for it. So M1, M2, and M3. I just go back 1. That's M1, that's M2, and that's M3. Okay, and very similar to before. Calculate the first Bezier curve using M1, using the first 3 control points. For the next, I don't know how many n Bezier curves, we just loop it through and using the symmetric basis function as before. Notice I'm always adding the Bezier curve to the end of S. And for the last one, we just use M3. And hopefully if it doesn't crash, I'll use MATLAB to show you the same thing again. Okay, so this time, as I get to the 4th one, you can see it extends right from the beginning to the end. And as I keep clicking, you know, I can just keep clicking randomly, and it's starting to slow down a wee bit. Yeah, it's not liking this at all. As you can see, very, very easy just to draw to your heart's content, that B-spline. Okay, I'm not going to lie, B-splines are difficult when you first encounter them. But lots of annoying algebra, lots of very tedious algebra, but it just comes down to this. Okay, so that symmetric one, the one in the middle. For the first 3 control points, you use that one. For the last 3 control points, you use that one down there. Okay, right, so you've been sat there quite doing, just listening to me babbling on. What I want you to do